In this section, 1.4, we're going to look at patterns and sequences. Typically, a pattern is just an arrangement of numbers, letters, figures. When we have an ordered arrangement of numbers, letters, or figures, we would call that a sequence. And we can classify sequences in a couple of ways. We can have a sequence that's arithmetic, and that is if we're looking at a sequence of numbers, we notice that the difference between each consecutive pair of numbers is the same. So if we look at the example here, we can see that we have 5, 9, 13, 17. So the difference between each consecutive, between 5 and 9 is 4, between 9 and 13 is 4, 13 and 17 is 4. So this here is an arithmetic sequence because we add 4 each time to get the next term. The next example, 20, 17, 14, 11, is also an arithmetic sequence. We're adding a -3, so it's going down by 3 each time. So sequences where we add or subtract the same amount to the number before it, or to get the next number, are called arithmetic sequences. The other type of sequence we have are geometric sequences, and this here is where they have the same ratio between pairs of consecutive terms. So if we take term 2 divided by term 1, we get the same ratio as term 3 divided by term 2. You can also think about it as you multiply each number by the same amount each time. So in this pattern here, we have 1, 3, 9, 27, 81. We can see that we're multiplying by 3 to get the next term each time. Or we can look at consecutive terms and divide them and see that the answer is 3. In the second example of a geometric sequence, 1, 2, 4, 8, 16, we can see that we're multiplying by 2 each time. So arithmetic sequences, we're adding the same amount. Geometric sequences, we're multiplying. And then if we have a numerical sequence that doesn't fall into either one of these, we would just say neither. So besides being able to determine whether a sequence is arithmetic, geometric, or neither, we're going to need to be able to generate the formulas for the sequences to help us solve problems down the road. So for both geometric and arithmetic sequences, we have two formulas. We have a recursive formula, which helps us find the next couple of terms, and then we have the explicit formula, which will help us find terms way off from our sequence, so maybe 100 places out. So some terms you need to know here is a sub n means the nth term. Our textbook also, instead of using a sub n, it will say the next term. So you can either use the word next or you can say a sub n. A sub 1 is the first term. N is the number of terms, so if your sequence has 5 terms in it, 5 terms long. D is the common difference. And then the other thing I want to point out to you is this a sub n minus 1. A sub n minus 1 is the same thing as previous, the previous term. So if a sub n is the next term, if I go one before the next term, that's the previous term. All right, so let's take a look at the recursive formula. The recursive formula here shows how to find the next term. One part that's missing here is that all recursive formulas should have the starting term. So you should also include a sub 1 equals and whatever that is. So let's apply that recursive formula to the sequences we have off to the right here. So number 1, I have the sequence 35, 32, 29, 26, 23. I can see that my sequence is decreasing, and it looks like I'm decreasing by 3 each time, right? 35 minus 32 is 3, 32 minus 29 is 3, 29 minus 26 is 3. So I would say that my constant difference is a -3. I'm going down by 3. So to write my recursive formula, all that I need to do is I need to record the first term. So I'm going to say a sub 1 is equal to 35. And then I'm going to say a sub n is equal to a sub n minus 1. So this here is saying that the next term is equal to the previous term plus the d value, which is -3. So in your recursive formula, there's only two things you need to replace. You need to fill in what a sub 1 is, and you need to fill in the d value. Let's look at number 2. In number 2, I can see that my sequence is increasing by a little bit. It goes from 1.5 to 2, so that's a 0.5 increase. From 2 to 2.5 is a 0.5 increase. From 2.5 to 3 is 0.5. So I would say that my d value is equal to 0.5. So I'm ready to write my recursive formula. I'm going to record the first term in my sequence, and that first term is 1.5. Then the second part of my formula is going to be the next term, so a sub n is equal to the previous term, a sub n minus 1, plus whatever my d value is. And here my d value is a positive 0.5, so it's just plus 0.5. So a sub 1 is equal to 1.5, a sub n is equal to a sub n minus 1 plus 0.5. So again, just two pieces that need to be filled in. If I look at sequence number 3, sequence number 3 looks like it's getting bigger, right? -5 to -1, that's adding 4. -1 to +3, that constant difference is 4. From 3 to 7 is 4. So it looks like my d value is 4. So to write out my explicit formula, I'm going to say that a sub 1 is equal to -5. That's what my first term was. And then a sub n, my next term, is equal to a sub n minus 1, the previous, plus 4. So that's the recursive formula. For the recursive formula, you just need to fill in two pieces of information, the first term and the constant difference. Now we're going to look at the same three sequences, but write them in the explicit formula. For the explicit formula, the same is going to hold true. We only need to replace or fill in the d value and a sub 1 each time. So if we take a look here at sequence 1, we already know that this sequence here has a constant difference of -3. So when I rewrite my formula, I'm going to say that a sub n, the next term, is equal to a sub 1, that's my first term, and we said that is 35, plus n minus 1 times the d value, which is a -3. And then what we can do here is we can simplify. So we can say that a sub n is equal to, if I distribute this -3 through, I'm going to get -3n plus 3, and then plus that 35. So it looks like it's going to be -3n plus 38. I don't care what you do. You could either leave it in this form here, or you can simplify it all the way down. It's up to you. Eventually we'll have to do some solving, so it might be helpful to simplify it, but you don't have to. If we look at sequence number 2, we remember from above that that constant difference was 0.5, and we can go ahead and plug that into our formula. So I can say that a sub n, the next term, is equal to the first, in this case it's 1.5, plus n minus 1 times the d value, and in this case that d value is 0.5. So if we were to simplify that, we would get a sub n is equal to 1.5 plus, distributing this through will give us 0.5n, and then minus a 0.5. And that would simplify all the way down to being 1.5, I'm sorry, not 1.5, it would be 1.5 minus the 0.5, right? So we're going to combine these two. It would give us 1 plus 0.5n. All right. And then for our last one here, I'm going to make a little room here, so I'm going to need to erase this here a little bit. our next sequence that we're looking at is getting larger. And we recall from the number 3 sequence above that our constant difference was 4. So D is equal to 4. When I plug it into my explicit formula, I get A sub n is equal to, my first term is negative 5 plus the quantity n minus 1 times that 4. And then if I distribute that 4 through, I'm going to get A sub n is equal to 4n minus 9, or plus a negative 9. Again, you can leave it this way or you can simplify it. So for our geometric sequences, we have 2 formulas again. We have a recursive formula and we have an explicit formula. The recursive formula, you have A sub 1, you got to find that first term. And then we have A sub n, which is our next term. A sub n minus 1 is the previous term. And r is going to be our ratio. So just like the problem we looked at earlier, there's 2 things we plug into this formula. We need to find the first term and we need to find our r value. R is the ratio. So let's go ahead and look at an example here. We can see in our sequence here we have 3, 9, 27, 81. So our sequence is increasing rapidly. I can see that I'm multiplying by 3 each time. So my ratio, 81 divided by 27, is 3. So when I go to write out my explicit formula, or my recursive formula, I need to record the first term, and so that is A sub 1 is equal to 3. And then my next term, A sub n, is equal to the ratio, which you said is 3, times A sub n minus 1. So basically what this says is that my next term is equal to 3 times my previous. So let's look at the second sequence. This sequence here is going down, but it's going down rapidly. So if I was to take my ratio of 45 divided by 225, or 9 divided by 45, or 1.8 divided by 9, I would find out that I'm dividing by 5, or I'm multiplying by 1/5 each time. Because it's a ratio that we're looking for, instead of saying divided by, we're going to multiply by that fraction. So here, my ratio is 1/5. So to write out my recursive formula, I'm going to say my first term, so A sub 1 is equal to 225, and then my next term, A sub n, is equal to 1/5 times my previous term, which is A sub n minus 1. So just 2 pieces are being substituted in. So then the same thing is true for my explicit formula. My explicit formula, I have an A sub n, which is my next term. A sub 1 is my first term. I need that. I need to figure out what r is, and it's to the n minus 1 power. So if I look at my sequence, the same one as number 1, I know that my ratio here was 3. I was multiplying by 3 each time to get the next term. So my formula is going to look like A sub n is equal to the first term, which is 3, times my r value, which is 3, to the n minus 1 power. If I look at example number 2, or sequence number 2, I know that my ratio was 1/5. So when I write out my formula, it's going to be A sub n is equal to my first term, which is 225, times my r value, which is 1/5, to the n minus 1 power. So whether it's a recursive formula or the explicit formula, for both of them, the only thing I need to substitute in is A sub 1 and r, A sub 1 and r, and the other variables are going to stay in. Let's practice identifying whether a sequence is arithmetic, geometric, or neither, and then we're going to go ahead and apply some of those formulas. So if we look at our first sequence here, we have 2, 20, 200, 2,000. The numbers are getting large pretty rapidly, which will indicate to you that you're probably multiplying. If we look at the ratio here, 20 divided by 2 is 10. 200 divided by 20 is 10. 2,000 divided by 200 is 10. So we have a constant ratio. We're multiplying by 10 each time. So we would classify this particular sequence as a geometric sequence. So the ratio was 10. And we would classify this here as geometric. If we look at sequence number 2, we have it decreasing, 56, 52, 48, 44, but it's decreasing pretty slowly. So I'm going to first check to see if there's a common difference. 56 minus 52 is going to give me 4, so I'm taking away, subtracting 4. 52 to 48 is taking away 4. 48 to 44 is taking away 4. So I have a constant difference of 4, negative 4. So because there's a constant difference here, we're going to classify this particular sequence as arithmetic. In number 3, we have 1, 4, 9, 16, 25. If we look at the difference, so 1 to 4, 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7. So the differences are different each time. If I look at the ratio, 4 divided by 1 is 4, 9 divided by 4 is going to give me 2 and 1/9, so the ratios aren't the same. So because I don't have a common difference or a common ratio, we would classify this particular sequence as a neither. What I do want you to notice, though, that this sequence here is a special sequence, and if we look at the numbers, we have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So it's really a sequence of squares. All right, if we move on to sequence number 4, we have 7, 10, 27, 37, 47. Looks like we're just counting by tens, right? So here we're adding 10, adding 10. So we have a constant difference of 10, and that would allow us to classify this particular sequence as arithmetic. If I look at sequence number 5, I have 1, 1, 2, 3, 5, 8. So it's increasing, but it's increasing slowly. If I look at the difference between terms, 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 2 is 1, 5 minus 3 is 2. So the difference isn't the same. If I look at the ratio, 1 divided by 1 is 1, 2 divided by 1 is 2, not a constant ratio. So I don't have a constant difference and I don't have a constant ratio. So that tells me that this sequence here is neither. This sequence here is also another special sequence. It is called the Fibonacci sequence, and we will take a look at that one in class on Tuesday. Then if we look at our last sequence here we have 8, 4, 2, 1, 1.5, so I'm decreasing. 8 minus 4 would be taking away 4. 4 minus 2 is 2, so it's not a constant difference. If we look at the ratios, I can take 8 divided by 4, that is 2, so really 4 over 8 would give me a ratio of a half. If I multiply it by a half, 4 times a half would give me 2, 2 times a half would give me 1. So here I have a ratio of 1/2, so I'm multiplying by the same amount each time. If I have a common ratio, I have a geometric sequence. So we identified whether a sequence was arithmetic, geometric, or neither. Now we want to go to the next column and look at some of these sequences and try to apply the formula. So In number 1 here, we're looking for the 12th term in the sequence. So if we look at this sequence here, we determined earlier that the sequence here was geometric and that it had a ratio of 10. So we have the first term, second term, third term, fourth term. We could keep multiplying by 10 until we get out to the 12th term, or we can use our explicit formula. The explicit formula for a geometric sequence is a sub n is equal to a sub 1 times r to the n minus 1. So here we're looking for the 12th term. That's my n value. So I'm going to put a sub 12 is equal to the first term in my sequence, which is 2, times the ratio, which is 10, and then I'm going to go to the n minus 1 power. N is 12. 12 minus 1 power. So I'm going to look at the 12th term is 2 times 10 to the 11th power. That's going to be a pretty big number, and unfortunately, I don't have my calculator with me, so I'm going to let you figure that one out. In number 2, we can see that that sequence was determined to be arithmetic, and we said that the common difference was negative 4. This time we're looking for the 30th term. So for an arithmetic sequence, the formula we have is a sub n is equal to a sub 1 plus n minus 1 times the d value. So because I'm looking for the 30th term, I'm going to look at a sub 30 is equal to the first term. The first term in this sequence is 56 plus n minus 1. I know my n value is 30, so 30 minus 1 times the d value, which we said was negative 4. So when I go ahead to simplify this, I'm looking at a sub 30 is 56 plus 30 minus 1 is going to be 29 times that negative 4. Again, I don't have my calculator, so I won't be able to simplify that, but I'll let you simplify that to find the 30th term. If we look at number 33, we want to find the 25th term in the sequence. When I look at this sequence here, we had determined that this one here was also arithmetic. We were adding 10 each time. So here I know that I have an arithmetic sequence. The constant difference was 10. So when I go ahead and apply my explicit formula, I'm going to look at a sub 25 is equal to the first term, which is 7, plus the n minus 1, so I have 25 minus 1, times the d value, which is 10. So I'm looking at 7 plus 24 times 10. I can do that calculation in my head, so I'm looking at 7 plus 240. So my 25th term is going to be 247. Okay, and then if I look at my last sequence way down here, I'm looking for the 10th term in this sequence. And this sequence was the 8, 4, 2, 1. And we said that that sequence was a geometric sequence, and it had a ratio of 1/2. So if I go back up to the top here and look at my geometric explicit formula, I'm going to say that a sub 10 is equal to the first term, which is 8, times my ratio, which is 1/2, and it's going to be to the 10 minus 1 power, which would be the 9th power. So I'm looking at 8 times 1/2 to the 9th. In this last slide, we're going to practice a little bit more on applying these formulas. In this first problem here, it gives us a sequence. We have 4, 7, 10, and then the dot, dot, dot means there's some terms in between there. We don't know how many. And the ending of my sequence is 88. And the question is asking us how many numbers are in the sequence. So I know what the first term is, I know what the second term is, I know what the third term is. I have a bunch of terms in between, and I don't know what the position of 88 is. So I need to first decide whether my sequence is arithmetic or geometric. I can see that from 4 to 7 I'm adding 3, 7 to 10 I'm adding 3. So because I'm adding the same amount, I'm going to say that it's an arithmetic sequence. And the explicit formula for an arithmetic sequence is a sub n is equal to a sub 1 plus the quantity n minus 1 times d. So I'm really trying to find the position of 88. So I'm going to say that this is my ending term, and so what I'm going to do is I'm going to substitute 88 in for my a sub n. So I have 88 is equal to the first term, which is 4, plus n minus 1, I don't know what that is, and then my d value, I said I was adding 3 each time. So then what I'm going to need to do here is I'm going to need to simplify. So I see that I have 88 is equal to 4 plus 3n minus 3. So I have 88 is equal to 4 minus 3 is 1 plus 3n. And I want to go ahead and solve. So I'm going to try to get the 3n by itself. So I'm going to subtract 1. So I have 87 is equal to 3n. So then n is equal to 87 divided by 3. 87 divided by 3 is going to give me 29. So I know that there are 29 terms in this sequence. All right, if we look at number 2 and try to read over what I've written, it says determine how many numbers in this sequence are less than 500. So we're trying to figure out how many numbers are less than 500. So if I look at my sequence here, I have 9, 18, 36. So 9 times 2 is 18. 18 times 2 is 36. So it looks like I'm multiplying by 2 each time, which tells me I have a geometric sequence. So if I look at the explicit formula for a geometric sequence, that explicit formula is a sub n is equal to a sub 1 times r to the n minus 1 power. I want to figure out how many of them are less than 500. So I have a couple of options. I could go ahead and just generate my sequence. I have 9, 18, 36, and I could just keep doubling, 72, 144, 288, and then when I double that one, I end up getting 576, which would be over. So I have 1, 2, 3, 4, 5, 6 terms are less than 576. I could also, if I wanted to, instead of generating, I could go ahead and plug in the information that I know. So here it says a sub n, which is my last term, and so I'm going to set that to be 500. A sub 1 is 9, the r value is 2, and I have n minus 1. So if I take 500 divided by 9, I have 55.5 is equal to 2 to the n minus 1. So here we could use some logarithms and take the log of both sides if you want to do that. Or you can just test out different n values to see what will get you close to 55. I know that if I take 2 to the 5th, that's equal to 32. 2 to the 6th is equal to 64. So since 64 is too high, we know we're looking at 2 to the 5th. However, we notice that it's n minus 1, so I need n minus 1 to give me the 5, which tells me that my n value then would need to be 6. So my n value here is 6. 6 minus 1 would give me the 5. So 6 terms is what we're looking at. So hopefully in this section you learned how to identify whether a sequence was arithmetic, geometric, or neither. And you've also been able to apply and use both the explicit and recursive formula for both the arithmetic and geometric sequences. If you go to Moodle, you should find a link for Nearpod where you can try out and check your understanding of these formulas.